Delaware Tech, Chemistry 100, Chemistry 110, Autoionization of water. We already know that water can act either as a weak acid or as a weak base. When there's a base present, water will act as a weak acid. When there's acid present, water will act as a weak base. But the fact is, water can also act as a weak base and a weak acid with itself. Two waters can interact. One can act as a weak acid. One can act as a weak base. The fact that it can act as either an acid or a base is called amphoteric, which is from the Greek for both of two. It's also known as amphiprotic, protic referring to the proton in the acid. So amphi means both, so it's both ways of using the proton. So we know that water can dissociate, and this is a very weak dissociation. Since water is a very, very weak acid, only an incredibly tiny fraction of water will dissociate into an H+ ion, a proton, and hydroxide ion, OH-. And more properly, we would write this as two waters, because anytime you have an acid, even if it's a weak acid, you always react it with water. So it's water plus water gives a hydronium ion, not the proton, because hydronium is always going to react with another water. A hydronium ion plus hydroxide. So one of our products is, in fact, our conjugate acid of water, and one of the products is our conjugate base of the other water. And this process of splitting up, ionizing two different waters in two different ways is called autoionization of water, or self-ionization of water. And here's a little GIF file that shows you have two waters. The oxygens are shown in red, and the hydrogens are shown in kind of a whitish gray. And you can see you start with two H2Os, one on the left and one on the right. And the one on the left comes over and steals a proton from the one on the right. And as a result, we end up making hydronium ion on the left, H3O+ on the left, and hydroxide, OH- on the right. Now, the charges aren't shown here, but you have to understand the charges moved with them. And this is what's going on in the autoionization of water. A tiny, tiny fraction of water does this all the time. So it's a very small amount that's associating, and as a result, the equilibrium for these two favors strongly the left side, but it is still important. And so in a neutral solution, the amount of hydronium, or protons, as I've written it here, remember hydronium and protons are the same thing, the amount of hydronium ion concentration will exactly equal the concentration of the hydroxide ion. And in fact, when they're both equal at normal temperature, about 25 degrees centigrade, that concentration will be 1 × 10⁻⁶ molar. In other words, about 1/10 of a millionth of a molar of the water at any one time will be ionized. And both of these concentrations will be exactly the same. That is pH 7. And by the way, pH 7 comes from the fact that if I take this number and I take the logarithm of that, I will get -7, and the pH is actually equal to the negative logarithm, which would be +7, or just 7. So that's why it's called pH 7, and that's where it comes from. That will be discussed in another module. So water can have a variety of concentrations. They can vary. So if you had a lot of acid, a lot of protons, the hydroxide concentration would be low. If I had a lot of hydroxide, the proton concentration, or hydronium ion concentration, would be low in response. But the product of those two, when I multiply the two concentrations together, no matter which each of them is, if I multiply them together, I will always get the same value, 1 × 10⁻14 molar squared. Remember, each of these is in molar, so molar times molar is molar squared. So the beauty of this is if I know the concentration of the hydronium ion, or the proton, that's the same thing, I can easily calculate the hydroxide concentration and vice versa, because I know that multiplying these two together will always give me the same number at 25 degrees. Now, I'll tell you at other temperatures the number varies a little bit, but we're not going to worry about that. You're always going to assume your problems at this level will be at 25 degrees. So this equilibrium constant, and let me explain why I call this an equilibrium constant. Remember, we talked about equilibrium. let's look at this reaction here. The equilibrium constant for water would be the concentration of the hydronium ion times the concentration of the hydroxide ion. Sorry for me going over the GIF file. Divided by the concentration of water, and we have two of them, squared. But remember, we never count pure liquids. So in fact, the equilibrium constant for this reaction is just the hydronium ion concentration times the hydroxide ion concentration. And because this is a special kind of equilibrium constant for water, we call it the Kw. It's also referred to as the ion product constant. It's called the autoionization constant. There are probably 2 or 3 other names for it, but most of us just call it the Kw. So the ion product constant, Kw for water, remember it's based on this equilibrium and the equilibrium constant calculated from this. It's always going to be equal to 1 times 10 to the minus 14 molar squared, as long as we're dealing at around room temperature. So what this means is that if the proton concentration is greater than 1 times 10 to the minus 7, remember 1 times 10 to the minus 7 would be neutral concentration. If it's greater than that amount, then the hydroxide must be lower than that amount. And if the proton concentration is lower than that amount, in other words, it's basic, it's low acidity, then the hydroxide concentration must be higher than that concentration. And if the two are equal, then we call it neutral. And the only time it's neutral is when they're both equal to 1 times 10 to the minus 7 molar. So if somebody tells you it's a neutral solution, you know 2 things. The pH is 7 exactly, and the concentration of both the proton, or hydronium, and the concentration of the hydroxide are the same, and they're both equal to 1 times 10 to the minus 7 molar. At any other pH, the 2 concentrations are going to differ. So as I said before, if we know the hydroxide concentration, we can just put it into this rearranged version of this formula, and we can get the proton concentration. Likewise, if we know the proton concentration, we can divide Kw by that, and we can get the hydroxide concentration. So if you know one, you automatically know the other value. And that's the beauty of this.